Hi there, Mr. Sutton here, bringing you the BC Calculus 710 Extra Practice number 4 solutions on alternating series test. For this problem, we're trying to find the interval of convergence for this series. Since this is not a geometric series, we're going to use the ratio test. So I'm going to have the limit as n approaches infinity of absolute value of n plus 1th term over nth term. So that means I'm going to have x to the 2 parentheses n plus 1, or 2n plus 2, I guess you could write it, over we have a 2 times parentheses n plus 1, or also 2n plus 2. So I'll distribute that in just a moment. Now the nth term is just the stuff in here. And notice I didn't bother including the negative 1. I mean, why bother? Because we've got this absolute value here. So this negative 1 won't really matter in the end anyway. Okay, so now I'm going to do a little same change flip to reduce this fraction. And I'm going to simplify at this point. So I'm going to have an x to the 2n plus 2 times 2n in my numerator. And downstairs we have 2n plus 2 in a parentheses times x to the 2n. These x terms can cancel out, or at least reduce. If I subtract the exponents, I just end up with an x squared in the numerator, along with the 2n that was already there. And we also have this 2n plus 2 downstairs. As n approaches infinity, I can actually ignore this plus 2. So this ends up being a 2n x squared over just 2n, which means I can cancel the 2n's, leaving me with just x squared in absolute value. And now I know that in order to converge the nth ratio for this series, namely the absolute value of x squared, this has to be less than 1. So solving for x, I can square root both sides. So absolute value of x is going to be less than 1. And then I can rewrite this without the absolute value as negative 1 less than x less than positive 1. Now I'm not out of the woods yet on this one, because since I used the ratio test to come up with this interval of convergence, we still have to test the endpoints. We don't know whether or not we actually converge at the endpoints. So this is kind of like a question mark, negative 1 to 1 situation. So at this point, we're going to plug in negative 1 and positive 1 into the function up here and see if that series that results converges or diverges. So in both cases, since the only place you're plugging in x is right here, and you basically have an x squared then being raised to the n power, since this is guaranteed to be an even exponent, it actually doesn't matter whether you plug in negative or positive 1. In both cases, you're actually going to end up getting the same result. Whichever of those you plug in, this is going to just become 1. And then you've just got this negative 1 to the n plus 1 left over in the numerator, and you have just this 2n downstairs. So this is an alternating series, and because the denominator is growing while the numerator is not, we're decreasing an absolute value to 0. Because of this, we can use the alternating series error test on, or alternating series test on this. By the alternating series test, this is going to converge, which means that we are converging at both of our endpoints, so we can rewrite this as negative 1 less than or equal to x less than or equal to 1. For this problem, I'm trying to find the interval of convergence of the derivative f prime of this function here, so be careful. We don't care about the original function. We want the derivative's interval of convergence. So let me start by getting the derivative. I'm going to write this in summation form, and I'm just going to take the derivative of this general term here. So using my power rule and treating n as a constant, that's going to be n over n squared, which is really just 1 over n. And we have an x minus 2 to the n minus 1. And I'm going to make that summation go from 1 to infinity. So now I have to figure out the interval of convergence for this. Since this is not a geometric series, I have to use the ratio test. So I got the limit as n approaches infinity of absolute value of the nth ratio. So n plus 1 over n is what my ratio looks like. The n plus 1 term of this is going to be x minus 2 to the n over n plus 1. For the nth term, I'm just using the summand, pretty much cut and pasting it exactly the way it already is. And let's multiply by the reciprocal to simplify this. So I've got x minus 2 to the n times n. And I've also got an n plus 1 and an x minus 2 to the n minus 1. I can reduce these x minus 2 factors here Subtracting my exponents, I've got x minus 2 to the n minus n plus 1, so I end up with an x minus 2 to the first power in the numerator, along with the n that's already there. And down here I've still got this n plus 1 hanging around. Now as n approaches infinity, I can ignore this plus 1. So I essentially have n x minus 2 over n. N's are going to cancel, leaving me with just x minus 2 in my absolute value. So that's my nth ratio. For the series to converge, this has to be less than 1. And I can now get rid of my absolute value and solve for x. So I'll rewrite this as negative 1 less than x minus 2 less than positive 1. Adding 1 to all three sides, we end up with 1 less than x less than 3. Or do we? Since we got this with the ratio test, we have to test the endpoints because we don't really know for sure if we converge there without testing them. So let's try out x equals 1 first. And by the way, we're plugging this into f prime that we wrote here, not the original series. So f prime, if I plug in x equals 1, that's going to be negative 1 to the n minus 1 over n. This is basically the alternating harmonic series. I mean, whether you write negative 1 to the n or the n plus 1, you've got an alternating series that would otherwise be harmonic. We know this one converges. And if we plug in 3 to the derivative here, this is 3 minus 2, which is 1, to the n minus 1 is all just 1 over n. That is the harmonic series, which we know diverges. So at the end of the day then, we have 1 less than or equal to x because we converged at 1, and then just less than 3 because we diverged at 3. To find the interval of convergence on this series, first we look to see if it's a geometric series. It's not, so we need to use the ratio test. So I have the limit as n approaches infinity of absolute value of the n plus 1th term, which is x to the n plus 1 over n plus 1, divided by the nth term, which is just this x to the n over n stuff they have there, the general term. And now let me just simplify this, multiply by the reciprocal. We've got x to the n plus 1 times n in my numerator. And then in the denominator, we have the n plus 1 here and the x to the n being multiplied. These x's can reduce a little bit, giving me just a single x in the numerator along with the n that's already there. And in the denominator, this n plus 1 is all that's left over. So as n approaches infinity, we can ignore this plus 1 down here. So I essentially have x to the n over n. N's cancel, leaving me with just absolute value of x. And now we know that to converge, the nth ratio, the absolute value x here, has to be less than 1. So rewriting that without the absolute value, we've got negative 1 less than x less than 1. And because we got this with the ratio test, we're not really sure that this is the true interval of convergence. I'm going to put a little question mark. And while I'm at it, I don't really need this limit up here. There we go. So yeah, we have a question mark here because I used the ratio test, so the endpoints are kind of ambiguous, but I can figure out what's going on there by plugging negative 1 and 1 into the nth term of the original series. So if I plug in negative 1, this is really going to be negative 1 to the n over n. That's the series that we're dealing with there. So that is just the alternating series, the alternating harmonic series, which we automatically know converges. It's known to converge. No proof needed. And then if we plug in 1 for x, we have the summation of, let's see here, this is 1 to the n, so just 1 over n. And that one is also pretty well known. That is just the regular harmonic series, which we know diverges. So then our interval of convergence, when all is said and done, we're going to have negative 1 less than or equal to x because we converged at negative 1. And then less than 1, no equals there because we diverged at positive 1. For this problem, I'm trying to find the interval of convergence for this series. Since this is not a geometric series, let me use the ratio test to get to the bottom of this. So I'm going to take the limit as n approaches infinity of the absolute value of the n plus 1th version of this divided by the nth term. So n plus 1 version is going to be 3x minus 1 to the n plus 1, all over n plus 1 quantity squared. And since we're doing all this in absolute value, I can forget about this negative 1 business. So now the nth term is what goes down below. That's just going to be all of this stuff without the negative 1 part in it. And now same change flip to try to reduce and simplify this. I've got 3x minus 1 to the n plus 1 times n squared in my numerator. In the denominator, I've got n plus 1 squared and 3x minus 1 to the n. These 3x minus 1s can reduce a little bit. That leaves me with just a 3x minus 1 in the numerator. Also, that n squared is still there. In the denominator, I got rid of my 3x minus 1 to the n. That pretty much completely canceled out. I do still have the n plus 1 squared, though. But don't worry, we're taking care of those n's, because as n approaches infinity, I can forget about this little plus 1 down here. So I essentially have 3x minus 1 n squared over n squared. N squareds are going to cancel, leaving me with just 3x minus 1 in the absolute value. Now to converge, the nth ratio that we just found here has to be less than 1. So let me solve for x in this situation. I'll start by getting rid of the absolute value with my double inequalities. So I have negative 1 less than 3x minus 1 less than 1. And then let me add 1 to all three sides. So that's 0 less than 3x less than 2. And then finally, dividing by 3, we have 0 less than x less than 2/3. Not the end of the story, though. Because I used the ratio test to get this, I don't know whether the endpoints actually converge or not. So I have to test 0 and 2/3 for x individually. So let's test out 0 first. If x equals 0, what do we get? Well, 3 times 0 minus 1 is just going to be negative 1 to the n here. If I've got negative 1 to the n times negative 1 to the n minus 1, that's actually negative 1 to the 2n minus 1, all over n squared. So that's kind of a weird situation. Now, before you look at this and use alternating series test, you have to be careful, because this 2n minus 1 is giving you odd powers no matter what. So this thing is always going to come out to negative 1 in the numerator, no matter what you plug in for n. But that's okay, because we do see that we have a p-series. We have a number over an n squared, basically. If you wanted to, you could factor a negative 1 out of this whole thing. And then you have 1 over n squared, which is a p-series with a p-value of 2. Since that's larger than 1, this is going to converge by the p-series test. Now let's also test out our other endpoint of 2/3. So if x equals 2/3, let's see what happens plugging that in. 3 times 2/3 is just 2. Minus 1 gives me 1. So this is 1 to the n, which we can pretty much just ignore. So all that's left over in that numerator then is negative 1 to the n minus 1, all over n squared. Now this does alternate. You're getting even versus odd exponents for every step you take here. So this alternates, and we're also decreasing an absolute value to 0, because you're basically doing something that's not growing over n squared, which is growing. So the limit as n approaches infinity on this one is going to 0. So because we alternate and decrease an abs value to 0, this is going to converge by the alternating series test. So therefore, since we converged on both of these, we can say 0 less than or equal to x less than or equal to 2/3.